Hello, guys, and welcome to episode 4 of Brainwave Boulevard. Today, we are going to learn about special relativity. The first thing I'm going to talk about is the difference between classical physics and relative physics, or modern physics, as people like to say. So, the first thing to note is that classical physics deals with speed or velocities that are much slower than the speed of light. And it deals with objects that are larger than atomic sizes. So that also deals with quantum physics and whatnot. For special relativity, one thing to note is reference frames. What is a reference frame? Let's say you are walking this way, right? No. No. You are looking at a stop sign, right? Let's say this is a stop sign. Now, I'm gonna draw a tree. If you're looking at this tree and you're like, is that tree moving? Subconsciously, your mind goes to the stop sign, and it determines, is the tree moving relative to the position of the stop sign? And you're like, no, it does not move like that. So, what if we use something like a dog? Let's say this is a dog, right? And let's say that's a dog. Now, the dog is moving this way at a velocity of 4 meters per second. To determine if the dog is moving, you look at the stop sign again, subconsciously. And what you will realize is that the dog moves. The dog is moving. The dog is moving. Like the dist I mean the position of the dog is moving relative to the position of your stop sign. Like the dog is moving. Look, the dog is moving. And that's what reference frames are all about. Okay. So, the next thing we have to know is the planes. So we have our X and we have our Y. And then we have our Z. But we also have the time planes, which are here and here respectively. And what you need to know is that inertial reference frames have velocity is constant. If we are looking at non-inertial, we are involving acceleration, which is just the change of velocity, such as changing directions or speeding up or slowing down. Now there's something. How should I explain this? We call it Galilean relativity, but in truth, it is really just simple math. Galilean relativity. Let's say you are moving inside of a train, right? And you're going this way at 3 meters per second. And the train is going this way at, let's say, 70 meters per second. How fast are you actually going? In truth, you are really going 67 meters per second in the direction of the train. But if we are looking at relativity itself, this does not apply. Because in here, with Galilean relativity, our velocity is constant. And we also have straight lines for our velocities. Okay, let's get to the first thing we need to know. The speed of light. Speed of light, which we denote as c, is equal to 3.000, well no, just 3 times 10 to the 8th meters per second. But it is also 2.997 meters per second. 2.997 times 10 to the 8th meters per second. Now, I would not recommend memorizing the 2.997. Just memorize the 3 times 10 to the 8th. And how we determine the speed of light is that c is equal to 1 all over the square root of naught and then mu naught. These variables you do not need to know. You do not know this. Do not know this. This is just like fun facts. But that these values deal with the breaking of free space with electricity and all that. Do not memorize that. Do not memorize that. You do not need to know that. Okay. Now, the two postulates of special relativity, which is different from general relativity. Special relativity, this deals with things where F net is equal to 0. And if you can recall, then F equals to ma, right? And this is Newton's second law. What this means is that we have no acceleration. A is equal to 0. That means our v is constant. Yeah, v is constant. And that we have no absolute reference frames. Okay, now the next thing we're going to talk about is Minkowski's space-time, where there is no absolute simultaneously. Absolute simultaneity. T is equal to now is a different from the Earth to anywhere else in the universe. For example, the sun. Why this works is because we have something like this. We have R is equal to C delta T. And C, of course, is the speed of light. Delta T represents time. So this literally represents space-time. And what this means is, if you recall I think I just deleted it, but if you recall, we have the planes. We have X, Y, Z, and then we have time, which adds a whole new layer to positioning and whatnot. Because you are not where you were 10 seconds ago, even if you are sitting in the same spot. Because time moves forward. The next thing we are going to be talking about is time dilation. Now, I think this is really cool. I'm gonna draw an example for this. So, let's say this is the Earth. And imagine this is the atmosphere. And this is outer space. Now we have the sun. And the sun rays hit the atmosphere. What happens is that we have particles that end up becoming energized, and they end up going towards the Earth, basically. Which sounds scary. That sounds scary. We have particles that are getting energized by the sun that are going at the speed of light and heading towards Earth. What's happening? What's actually happening? what is happening is that this particle is called a muon. Muons are just particles, any type of particle that becomes energized by the rays from the sun. Now, the velocity of these muons is very close to the speed of light, and we denote that speed as 0.99 c or as 0.98 c, depending on the muon, of course, and circumstances. But what this means is that we record the time of the muon's life as 2.2 microseconds. And if you do the calculations, where the distance from here to here, blah blah blah, right? You find out the distance between the atmosphere and the Earth, you find that 2.2 microseconds is not long enough for an object moving at 0.99 or 0.98 c to actually hit the Earth. So what's going on? What's actually going on is time dilation. And the equation for time dilation is delta t is equal to proper time, which we denote as delta t of p, over the square root of 1 minus v squared over c squared. Now, this equation is pretty neat because if we just have, let's say, 0.99 c here, and we just, we plug it in, what happens is that we just get 0.99 over c, which is pretty cool. It's an easy simplification. Now, if we do this equation where proper time in this case is 2.2 microseconds, right? And we just plug in our values of 0.99 square. Wait, no, yeah, okay. Yeah, okay. It's just 0.99, I forgot. So it's just 1 minus 0.99 squared. And this ends up being around 16 microseconds. And that's actually the time that the muon experiences. What we see is 2.2 microseconds. But if we put ourselves in the shoes of the muon, it is in fact living for 16 microseconds. That's really interesting. So, if we analyze this equation further of delta t is equal to proper time all over the square root of 1 minus v squared over c squared, what if v approaches c? I mean, v is equal to c. Then what happens? We get our proper time, right? And then we get the square root of 1 minus, we essentially have c squared over c squared, which is just going to be 1. And this ends up being 0. But in truth, this actually means infinity. So if you are moving at the speed of light, you are technically immortal, as long as you do not change directions or you don't speed up or slow down. Now, the conditions of this, of not speeding up or slowing down or changing directions, it completely nullifies the twins paradox, which is if you have two astronauts where one remains on Earth and these astronauts are twins, if you have one astronaut that just goes way out, right? Just goes way out, and he's out in space, as long as this astronaut is not experiencing any net force or acceleration, then he is going to be younger than his twin brother at the current time, or at the current position, blah blah blah. If he turns back, this paradox does not work anymore because you just changed directions and you are no longer younger. You're going to be the same age because you turned around. And that's why the twins paradox does not exist. It's not real, despite whatever people say. Now, what if we have a v is less than c by a large margin, right? Let's say v squared is just equal to 1. I mean, yeah. Then we would have something like this. V squared, which is just 1 over c squared. And we can just say that this is equal to 0 because it's very small. Then we would have delta t p over 1, which is just delta t of p. And that means that our time is just proper time. So this follows the classical physics equation as well, which is pretty nice. Now, the next thing we're going to talk about is length contraction. So, I'm going to draw another example. Let's say we have the Earth and we have a spaceship. Now, let's say the spaceship is moving at an extremely high velocity. Let's say 0.75 c. If we say this spaceship in reality is about 15 centimeters, right? If we are on Earth and we look up at the spaceship, because we are on Earth and not moving at the speed of light, we cannot see the true length of the spaceship. Instead, the spaceship to our eyes is going to be something like 5 centimeters, which is smaller, right? And I just realized this is a very small size, but that does not matter. It is just an example. This equation for length contraction is pretty similar to the time dilation one. And I'm going to write it out real quickly, where we have length is equal to LP over this goofy little symbol, where symbol is equal to 1 over the square root of v squared over c squared. I mean 1 minus v squared over c squared. And this equation, if you saw it, is actually what we have in time dilation. So, yeah. So our equation is LP over the square root. Wait, no. LP times 1 minus v squared over c squared. If v is, let's say, very small again, then we have LP times 1 minus 0, which is just equal to LP. If we have v is equal to c, then we have LP is equal to 1 minus 1 again, and L is equal to 0. This means that if you are moving at the speed of light, your length is going to be 0. I don't know who wants to be 0 in size. But this also just means that it is also just impossible to do. So don't do it. Don't move at the speed of light. The next thing I'm going to talk about is relativistic momentum. Momentum, if you know, is P is equal to mv. Right? And this is classical. If we move to the relativistic, then we go that P of the rel is equal to mv over 1 minus v squared all over c squared, which is just equal to the goofy little symbol mv. If v is less than c, then P is equal to mv, which follows the classical. But if v is equal to c, then we have mv over 0 all over again, and that our momentum is equal to infinity. Now, now we have relativistic energy, where E total is equal to E quote unquote rel is equal to that symbol mc squared, which is just equal to mc squared all over the square root of 1 minus v squared over c squared. And we have Ke, which is kinetic energy, is equal to goofy little symbol mc squared minus mc squared, which is just equal to mc squared all over the square root of 1 minus v squared over c squared minus mc squared, which in truth is just mc squared times 1 over square root of 1 minus v squared over c squared minus 1. And that's the equation for Ke, or kinetic energy. Now we have ER, which is just relativistic. It's just mc squared, then Ke over rel is just equal to E total minus ER, which we just wrote in the previous layer. Then we have E squared of the total is equal to E squared is equal to P squared C squared plus MC squared squared. Then E total is equal to the square root of PC squared plus MC squared squared. Okay, what this equation tells us is that if at rest, or if V is equal to a very small number compared to C, that means E is equal to MC squared, which is just ER. If we have a photon, then things change, because we would assume that M is equal to 0. Then we would have E squared is equal to PC squared, and then we would have E is equal to PC H lambda C, which is equal to HC over lambda. Nice! Now, I'm going to be talking about a little bit of general relativity. This is just relativity where you can accelerate, which means you can change direction, speed up, slow down. I'm just going to talk about one thing, and that is how to calculate the size of a black hole. So, we have a special equation where Rs is equal to 2gm all over c squared. R is the radius, and the g is just a constant of gravity, a gravitational constant, which you can remember from the Newton's gravitational law, universal gravitational law. And what we know is that K of R is equal to negative gm all over c squared r cubed. Then negative gmc squared all over c4r cubed equals equal to negative g over c4. And then we have u over r cubed. And then we have that is equal to negative g all over c4 ug. This is just the curvature of space-time. Where we have something like this, right? And this is r. If we calculate using the sun for its mass, then we would find that the sun as a black hole would not be able to reach the Earth. That means that if the sun were to become a black hole, it would not affect the Earth in any particular way, and that the orbits, the orbits of all the planets would still be the same. There is nothing else to talk about with relativity. I've taught you the basics, and I hope you've had a learning experience with Brainwave Boulevard. Thank you for watching. Like and subscribe, please.